we sort of conveyed in the previous video, the error you make with linear approximation, namely how far you are from the actual value of f of x, is the absolute value of f of x minus the linear approximation. And so that's the error that you make in your approximation. Of course, if this is 0, it means that the value predicted by the linear approximation is exactly the same as the value of the function, in which case you're completely error-free. But as I said at the end of the previous video, more important notion is that of the percentage. Error, which is the error you make, which is a quantity we define up here. So the error is equal to that. So how far you are from the actual value of f, given point, and divided by the actual value, when the actual value actually makes sense, because if not, if it's 0, then you'll be dividing by 0. And you multiply that by 100%. So that gives you the percentage error. And to see, I mean, with an example, to see, I mean, how can we implement this when measuring how good our approximations are? Let's see what happens when we're given the task of approximating a trigonometric function like tan pi over 4 plus 0.02, and we're also asked to compute the percentage error. Well, the function f of x that we want to linearize here is tan of x, right? This is the tangent of x, and the point x0 is pi over 4, and so that means that the linear approximation at pi over 4 will be the function f at pi over 4 plus f prime at pi over 4 times x minus pi over 4. So that's a linear approximation. F at pi over 4 is the tangent at pi over 4, which from the previous example, even if you didn't remember it from before, but sine over cosine at pi over 4, but they're both equal to square root 2 over 2, so that gives you 1. And now f prime at pi over 4, well, we need to remember what the derivative of tangent is, which is secant squared. So we need to compute secant squared of pi over 4. But secant squared, what is secant is 1 over cosecant, no, 1 over cosine squared, I'm sorry. So this is 1 over cosine squared of pi over 4, and that's the same as, well, 1 over square root 2 over 2 squared, so 1 over square root 2, which is just 2. So a linear approximation is given by 1, which is the value of f at pi over 4, plus 2. 2 is the value of the derivative, times x minus pi over 4. Okay, so this is our approximation of the function, a linear approximation, and we are now asked to compute the percentage error that we make when we when we use this substitute for the actual value of the function. Okay, so at x equals pi over 4 plus 0.02, the approximation we have is 1 plus 2 times 0.02. We just plug this value into here, okay? And this gives us 1.04. Here is a point I want to make for the in the next problem, and I want to draw your attention to this. So how are we supposed to know the percentage error if we don't know the value of the function? So how can you give a value of the percentage error if you don't know what you're trying to approximate to begin with? So if you actually knew the value of the function, you would know, I mean, you wouldn't need to approximate it at that point. Okay, well the thing is, we actually give a bound. In general, what we can do is to give a bound of for the error. So even though we may not know the actual value of the function, we may control other quantities that help us estimating the error. This is what we're going to do in the next example. For now, the only thing we're trying to do is to provide the percentage error, assuming we know the value of the function at the point. So here, the tangent of pi over 4 plus 0.02 is 1.008, etc. And so this implies that the percentage error is approximately equal to 1.0408, which is the value of 10, minus 1.04, which is the value predicted by the linear approximation, and that divided by the actual value, so again 1.0408, and then times 100%. So if you compute this quantity inside, you get something that's close to 0.08%, which is quite small. So our approximation is very good. Even when you take into account the percentage error, which measures how big is your error compared to the actual value of the function. Okay, so as I said here, I mean, we know, because we know the actual value of the function, we can tell the percentage error is very small. what happened if we didn't know that? And that's kind of the point of the application. Well, it turns out that the error made when you use the linear approximation can be bounded from above if your function is twice differentiable. Okay, so the error if you go back to the definition of the error, is f of x minus L of x. What is L of x? Is f of x naught minus f prime of x naught times x minus x naught. So it is natural to think that, okay, how do we approximate f of x? Well, we consider the value at a nearby point, then look at the tangent line to look at the derivative at that point, and we approximate this thing linearly. And so what we should be left with, if you remember the example with the area, with something that depends on the square of x minus x naught. And it turns out that, and also, here the second term involves the derivative of f. So you have something that has two derivatives. Turns out we can bound this by k minus, and that's k times x minus x naught squared divided by 2, where k is the maximum value of f double prime in absolute value on the interval from x naught to x naught plus delta x. Okay, so I believe that things up to this point should be clear. You have some definitions. You know how to find the linear approximation at a given point. You just need to know the value of f and the value of the derivative of the point. You also have, you can compute the error just by subtracting the actual value of the point and the value predicted by your approximation, if you happen to know the value of the function of the point. And then, if you happen to know the value function of the point, you can also compute the percentage error. So this appears in two places, here, here and here in this example. So what happens if you don't know the value of the function at the point? How can you estimate the error you're making? And so here's where you cannot say for sure what the error is, but you can give a bound on how big it can be. And that depends on how far you're from the point, so x minus x naught squared, so it's just much smaller than x minus x naught, when x minus x naught is small. And it depends on the maximum value that the second derivative takes in modulus in the interval between the point at which you're linearizing and x naught plus delta x, so the point you want to approximate. So let's see an example. What is cosine of pi over 2 plus 0.1 approximately equal to? This is approximately equal to, if we look at the linear approximation, remember we would need the value of the function at the point, cosine of pi over 2, and then plus cosine prime of pi over 2 times pi over 2 plus 0.1 minus pi over 2. And this is equal to 0. Cosine prime is minus sine, so it's minus sine at pi over 2. And this is equal to 1. So this should be approximately equal to minus 0.1. This is the approximation provided by the linearization, or the tangent line. And what is the error? What is the error that we're making? Okay, so let's look at something. We know that the error, according to this formula, is bounded by k times x minus x naught squared. X here is equal to pi over 2 plus 0.1, and x naught is equal to pi over 2. And so x minus x naught is 0.1. So we know the error. We know that the error is smaller than k times 0.1 squared divided by 2, where k is the largest possible value of cosine double prime of x for x inside the interval pi over 2 and pi over 2 plus 0.1. Right? What is cosine double prime? Cosine double prime is minus cosine of x. So the absolute value of cosine double prime is cosine of x. And no matter where we are actually, so it doesn't matter whether we're in this small interval or not, but cosine of x is always bounded by one absolute value. So cosine just goes from minus 1 to 1, then goes back down to minus 1, etc. So it's always oscillating between minus 1 and 1. It's always trapped between 1 and 1, so the absolute value is always less than or equal to 1. So there's our approximation. So in any case, we know that k cannot be greater than 1. Because the absolute value of cosine can never be greater than 1 anyway. Doesn't matter what interval you're looking at. Whether this interval or not, cosine of x in absolute value can never be greater than that. So that means that our approximation, or the error we make when we approximate using the linearization, or linear approximation, is going to be smaller than or equal to 1 times 0.1 squared over 2. And this is 0.01 divided by 2. So this is our error, which is actually quite small. See? We'll see another example in the next video.